Well, so the answer to today's quiz would be as follows. You will have to, if we have an extended body which contains a lot of charged particles, it is easier to calculate the electric field by dividing the body into differential pieces, and each piece contains already millions of particles, rather than calculating particle by particle. So this is an extended body with a certain charge distribution, and let's say that we want to find electric field at that location. dE is a contribution to the electric field at that location due to a differential segment of the body. K is Coulomb's constant, dQ is charge of that differential piece. R is the distance between the piece and the considered point at which we calculate electric field vector, and unit vector R is a vector indicating direction from that differential piece toward the point of interest. Well, now when we have when we find out, why are we looking for electric field? The purpose is really to determine the interaction of particles or objects which are placed in that field, and electric field vector leads directly to the electrostatic force. So, and we need that to calculate the net force and predict the future. Acceleration can be found from the net force. So in the consideration of interactions with other bodies, we need to calculate this electric field. All right, so let's see how a particle is going to move in an electric field, and we will talk just particular field, uniform electric field. Let me remind you that uniform electric field means that throughout the considered space, electric field vector has the same value. This type of electric field is produced between two parallel conductive plates. So, for example, like this. Imagine that this is one plate, horizontal, and this is another horizontal plate. In order to produce a field, we will have to connect it to appropriate power supply. And what would really happen, power supply would deliver charged particles to those plates. Minus indicates that it would charge this plate with a negative charge. And plus means that the power supply would charge this plate with a positive charge. And yesterday we saw that a plate or a plane produces electric field which is proportional to the density, surface charge density. Now let's say that if I have a positive charge on the top plate, and we have certain density sigma, charge density sigma, where sigma would be a positive number, and this will charge this plate with a negative charge, so density will be a negative number, and let's say that it's opposite to that other one, so it will be minus sigma. Then you can recognize now that electric field between the plates, if we recall what was electric field produced by a single plate, it was surface charge density divided by 2 times permittivity of free space. It was sigma divided by 2 epsilon 0. So now electric field produced by this plate will be downward, because electric field lines from a positive charge are heading away from negative, and they are heading toward negative. Now, electric field produced by the plates will be also downward, and its value will be, this time, magnitude will be again sigma over 2 epsilon. So if I add those two fields, the electric field between the plates really will be surface charge density divided by permittivity of free space. you can also notice that outside of those plates, like over here, well, electric field produced by the top plate is away, by the bottom plate is downward. I mean, so one is upward, one is downward, and they have the same value. So electric field above the plates is 0. Electric field below is also 0. So we have just electric field between the plates. And let's imagine, I mean, this is quite often a situation that if we produce some electric field and shoot charged particles, then electrostatic force is the only significant force. Really, the only competition is magnetic force. So in the presence of electric and magnetic field will have a significant contribution. But if electron travels, for example, simultaneously through gravitational field and through uniform electric field, gravitational force is negligible. Drag force could be significant. So if we try to shoot to take a place and try to shoot charged particles in air, they will not really travel well. It rather requires vacuum, so we would have to evacuate a tube with the plates in order to have charged particles to fly through it. So let's assume that we have a situation in which the only significant interaction is electrostatic interaction, which means that the only significant force would be this electrostatic force. And, well, let's say if we shoot in a particle which enters this electric field, how the force would depend on position. Think about it. Is it going to increase as it moves through the field? Is it going to, well, grow up and then down? Or is it going to be constant? Or is it going to decrease? Well, recall how force is related to the field. We have to multiply charge of the particle of the interest by electric field vector at the location of the particle. Now, if I consider a particle like an electron or a proton, what happens to this charge? Is it going to increase, decrease, or nothing? Let's say, who votes that it is going to increase? Who votes that it is going to decrease? Who votes that nothing will happen? Right. Charge of an electron cannot change. So let's now see how as particle travels through the field, how the electric field vector changes at the location of the particle. Well, obviously it is going to be also constant as long as the particle is between the plates. So electrostatic force is also going to be constant. Well, so from Newton's second law, we can figure out how the particle is going to move. We can recognize that electrostatic force is going to be charge of the particle multiplied by electric field at the location of the particle. However, in a uniform electric field, despite the particle changes position, electric field vector remains constant. So that electrostatic force is going to be constant. If electrostatic force is going to be constant, then acceleration of the particle is going to be constant. And specifically, it is going to be equal to that proportional to electric field. Acceleration is going to be proportional to electric field vector. It's going to be in the same direction as the field, and the proportionality is determined by the charge of the particle and mass of the particle. The heavier the particle, the smaller the acceleration, its magnitude, and the higher the charge of the particle, the stronger acceleration. Well, if we know acceleration, well, we can predict what will happen with velocity, provided that we know velocity at a particular instant. So let's say that we know velocity at initial instant, certain instant when we, well, let's say when we turn on our clock, and let's say that we turn on our clock when the particle enters the field. So velocity at an arbitrary instant t is equal to the velocity at particular instant plus integral of acceleration. It's an inverse relationship between velocity and acceleration, because acceleration was derivative of velocity. Well, then using first fundamental theorem of calculus, we can find out that velocity will be equal to such an expression, which involves integral of acceleration. And in case of uniform electric field, the integrated function is time independent, so I can take it in front and find an expression for velocity at any instant. Well, if I found velocity at any at an arbitrary instant, I can go further and predict where the particle is at an arbitrary instant. How do we do it? Again, using inverse relationships between velocity and position. Or from mathematical point of view, it will be using the first fundamental theorem of calculus. So it is position at a particular instant, and usually it is, in general, it doesn't have to be the same instant at which we know velocity. From mathematical point of view, it doesn't matter, but usually when we know those two quantities at the same time, velocity and position. So I can write down that position now at an arbitrary instant is initial velocity at instant 0 plus, not initial velocity, initial position, right? Initial position plus integral of velocity. And I can plug in the expression for velocity from here. Now note that this function is not constant anymore. It's a linear function of time. It contains a constant term and term linear with time. Using fundamental theorem of calculus, I can also continue calculation and find the expression for position at an arbitrary instant. Can you recognize these formulas? Have we discussed these? When? What kind of motion is that? A what? Motion with constant acceleration. All right, we also refer to this as starts with P. Projectile motion, correct. Yes, so the particle is going to travel along a curve which is a parabola, correct. I hope actually that this, I didn't actually test, so I'm not sure if it is going to work, but I hope that it is. A simulation. Yes, it does. Okay. So I have here a simulation in which I have two parallel plates, a charged particle, and I can control the field. So how about if we run it without electric field? The particle should travel which way? With a constant velocity. Correct. So the particle should travel with constant velocity, right. Let me erase the track. How about if I now change the field? Oops, I had to reset it first. Did I mark if the particle is positively charged or negatively charged? No, I didn't. Let's say that it is positively charged. Yeah, it is going to travel along parabola. And actually, the program calculated it consistently like a parabola. Now, let's say that if the particle had a positive charge, then this positive value This is positive value just for a component of the electric field, for the vertical component of the electric field vector. The other horizontal components, I marked them over here to be 0. So this is just a vertical component of the electric field. Well, consistently with the object which produces that field. Two parallel plates, two horizontal parallel plates will produce a vertical electric field. So what is the direction of electric field at this moment? Who votes that it's up? Who votes that it's down? Who votes that it's sideways? It's down, correct. If the particle had a negative charge, then we would need to, this trajectory would be created if the electric field were up. Actually, we can. For the same particle, now I will change the direction of the field. So it turns the other way. How about actually if I don't erase this, now I will not make that field as strong. So now electric field is weaker. How the trajectory will compare with that one? It will be more flat, correct. I hope so. And where is it? Okay. Yes, we got it. This is a simulation, but really you predicted the future. This is what physics is about. To design things which will work the way we want. All right. So far we used one quantity which to describe electric field as the region. Yeah, because electric field, I'm using phrase electric field as the space in which electrostatic forces are exerted. What physical quantity did we use to describe electric field? So far, only one. It's a tough question. Consult with you may consult with your neighbor to recall what physical quantity we used so far to represent the field and make predictions about the field. Let me give you a hint. To imagine that field, we use electric field lines, for example. Electric field lines geometrically represented electric field. However, they are useless for calculations. In order to do calculations, we use another physical quantity. We introduced another physical quantity which allows us quickly to find out, sometimes it could be quite time-consuming, but allows us to predict interaction in terms of force. What was the physical quantity which we used? Not charge. Charge is an attribute of a particle. Charge indeed led to the force, but it characterizes the particle, not the space. Electric field vector, correct. We use electric field vector to characterize electric field as the region of in space. Electric field vector, actually in today's, I think you have a lab today. Somebody has a lab today. So those of you who have a lab today, you will be actually trying to represent fields using electric field vector as well. But you will also use another physical quantity which is much easier to measure. Because try to figure out how would you determine what is the value of electric field vector at this location. What would you have to do? Well, you will need to grab some kind of test particle of known charge. Put it over here and measure what is the force exerted on it. It's not a trivial problem to find a particle. I mean, to isolate a particle. Now, when you isolate a particle, then you will have to think how to connect it to a scale so that you can measure that force. Practically, it's impossible. It's much better. I mean, you could, for example, determine this electric field vector between the plates by looking at the deflection of a beam of electrons. You can shoot a beam of electrons between the plates and see how far they deflect. From that, you could determine what's the electric field. But for that, you will need already a tube. Not mentioning that if the field is not uniform, it would be really hard to determine. It is much easier to measure another physical quantity, which also is used to characterize electric potential. And electric potential also leads directly to a certain physical quantity describing interaction, like electric field vector led to force. Now, after force, what other description of interaction we use in physics 1? Right after force, the second description of interaction in physics 1 was work, correct. And potential is a physical quantity which characterizes electric field, the region, and leads to work, or more precisely to potential energy, because potential energy was introduced for the purpose of calculating work. So I phrased this definition in a way very similar to the definition of electric field vector. I had to change few words in the phrase and the formula and get the definition of electric potential. So the electric potential at a certain position R is a number V of R such that the potential energy of a particle with charge Q placed at this position would be equal to the product of charge of that particle and potential at the location of the particle. Now let's see where we have the differences between the definition of electric potential and electric field vector. It started with the electric. Both definitions started with the electric. Now, this time we are defining potential, so instead of having electric field vector, we have electric potential. Both are at the same location, at a particular location. Here we have a difference. Electric field vector was a vector, electric potential is a number, such that there it's identical, and here we have the electric force, now we have the electric potential. The rest is the same, and the formula is different. We had force equals charge multiplied by electric field vector. Here we have potential energy of the particle is equal to charge of the particle multiplied by potential of the field at the location of the particle. How about if we try actually again to recall what is what? So U stands for potential energy. Which potential energy? Well, electric potential energy. Which electric potential energy? Of a particle, correct. Which particle? Placed at position R, correct. Now what's Q? Charge of the particle. Which particle? At position R, correct. Now what is V? It's what? Well, yes, a number. No, I mean, what physical quantity? It happens to be a number, yeah, but the quantity, yes, William? No, V is not the charge. V is the electric potential, correct. Which electric potential? Of the particle? Of the space, right. It's not of the particle. It is related somehow to the particle. How? It is at the location of the particle. We have to take, in order to find potential energy of a particle at a particular location, we have to multiply potential at the location of the particle. However, it is not potential of the particle. It's potential of the space. Sounds much better. Precisely, you should say that this is potential at the location of the particle. It characterizes the location. Potential characterizes potential. Potential energy, however, characterizes what happens with the particle when it is at that location. All right. The SI unit of electric potential is 1 volt, and actually from this expression we can relate it to the physical units we know from the past. So electric potential energy is measured in the same units as potential energy of any type, which means that the SI unit of the potential energy is joule, the same as work. Yeah, so potential energy is measured in joules. Charge is measured in coulombs. Therefore, potential will be measured in joules per coulomb. So 1 volt corresponds to joule per coulomb. If we connect all points in space which have the same potential, we will get a surface which is referred to as equipotential surface. And in order to measure potential, we have a very simple device. We call this device a voltmeter. Now, potential has the same property as potential energy. Now, where potential, think about gravitational potential energy. Where gravitational potential energy is 0. In other words, where do we assign, at what location? Is it, let's say, on this floor or floor up? It doesn't matter. What matters is that if we decide, if we choose a certain point in space to which we assign potential energy to be 0, we call that location a reference point, and then we are consistent. Our predictions about future will be correct as long as we are consistent. So I can say that now my gravitational potential energy is 0. So if I go upstairs, my gravitational potential energy would increase. However, it's okay to choose I could choose my gravitational potential energy on the next floor to be 0. Now I would have negative potential energy. But it would work. In both cases, it would work. All right. So we always, whenever we think about potential energy, we have to choose a reference for potential energy. So when we use a voltmeter to determine potential energy of at a particular location, we have to decide where we want to have a reference for potential energy. So let's say that I have a rod like this, and I can select one end as the reference for potential energy. On diagrams, you will have this symbol which would indicate that it is a reference for potential energy. And actually, this symbol says that this point is electric connected with the earth, with the ground. And commonly, you will even refer to this point as a grounded point, or simply ground. So in order to determine potential at particular location, I have to connect one terminal of the voltmeter and actually that lower potential, that minus terminal of the voltmeter to the reference point, and the other end of the voltmeter to the point where we are interested in the potential, and the voltmeter will display potential. Voltmeter, as the device, actually is used to measure something else than potential as well. It is used to measure potential differences between various points. It always measures potential difference between the points which you touch. So if it happens, then one end touches a point where potential is 0, then know that potential difference between these 2 points is equal just to potential at that point. Do you see that? So directly you will measure potential only if one terminal is connected to the reference point. However, you can connect it at to different points as well. Now, you probably heard the word voltage, although I prefer that for a while we don't use word voltage. Rather than voltage, we will use what it means. It is voltage is a, well, kind of, it's almost slang word. However, it is used so commonly that now it is accepted as the term referring to electric potential difference between two locations. So more precisely, rather than voltage, you should say potential difference. And I want you to say potential difference for at least a week. After that, you can switch to voltage, because the most common mistake with this quantity with potential is to confuse potential with potential difference. If I plug in, for example, 2 terminals of a voltmeter into a socket, I will measure quantity related to potential difference, not potential of the socket. Let's see. Oh, now because electric potential and electric field vector describe the same thing, they characterize the same thing. What? They are used to characterize the same thing. A what? The space. Electric field. Right? Electric field vector characterizes the space. Electric potential characterizes the space. You should imagine it somewhat differently. So, for example, how do we imagine electric field vector? How it characterizes the space? To each point of the space, or at each point of the space, we should imagine an arrow. Right? That arrow will represent electric field vector. Well, with electric potential, rather than having an arrow, we should think about a number, correct? So at each location we have a certain number. But they both characterize the same thing. And relationship between electric potential and electric field vector is related to the relation which links the corresponding interactions. In other words, a quantity describing interactions. This one leads to work. This one leads to force. So electric field vector and electric potential are related the same way as force and work. All right. So if we know electric field vector everywhere, we can find electric potential everywhere. It is that potential difference or differential potential difference between 2 points which are separated by a difference in position ds is opposite to electric field vector multiplied by ds. Note actually that it's similar to difference in potential energy. We have that as a particle moves from one location to another location, change in potential energy was opposite to the conservative work. And conservative work was force times displacement. It's exactly the same way as here. Now, if we know electric potential in space, we can also find electric field vector. Also, a formula very similar to this: how to calculate force from potential energy. Anybody remembers how to do it? Kyle, do you? How to calculate force from potential energy? Like, for example, gravitational potential energy, formula for gravitational potential energy states that gravitational potential energy is mass times acceleration due to gravity times elevation, times height, mgh. How from mgh find expression for weight? What do we have to do with mgh? Calculate the what? Gradient. Calculate derivative of it with respect to x, y, and z. Well, if we calculate derivative with the horizontal component of mgh, we will get horizontal component of weight. Now we see that mgh is in vertical direction, so think about that it's z. And so more precise, it will be mgz. So when we calculate x component or x derivative of mgz, we will get 0. When we calculate y component from mgz, we will get 0. When we calculate vertical component, we will get mg, and we have to put a minus, and we will get the vertical component of weight. Well, the same way, if we want to find out electric field from electric potential, we have to calculate the derivatives of electric potential with respect to each coordinate. I think that this will be the right place to end the lecture today. So see you tomorrow then.